Welcome all. In this lecture, we are going to learn about transverse magnetic mode in rectangular waveguide. So here is the rectangular waveguide, which is placed in the horizontally oriented x-axis and vertically oriented y-axis. Let us assume that our wave is propagating in positive z direction along this axis. And here is the cross-section area of this rectangular waveguide. If we talk about the breadth of this rectangular waveguide, then it is being represented by A, and the width of the rectangular waveguide is represented by B, and here the length of this rectangular waveguide is nothing but equals to L only. So this is all about the wave propagation and rectangular waveguide introduction. Now for the TM mode or the transverse magnetic mode to propagate in the rectangular waveguide, we have to assume that the Hz component is equals to 0 only. So the TM mode in rectangular guide are characterized by Hz equals to 0. So this is the most important condition which is associated with transverse magnetic mode. Since the Hz component is equals to 0, then we assume that the Ez component should exist in case of transverse magnetic mode in rectangular waveguide. And if we talk about the solution for the Helmholtz equation, then for the TM mode, the Helmholtz equation is given as del square into E of z, that is being equals to gamma square into E of z. This is our equation number 1. Since Hz component is 0, so the Ez component will be present. That's why the Helmholtz equation is represented in terms of Ez component. Since the one Helmholtz equation we already discussed in the lecture of solution of wave equation for rectangular waveguide, and that was given as del square into psi, that was equals to gamma square into psi. And if we talk about the solution of this equation, then it was equals to psi, that is given as A sine kx plus B cos kx multiplied with C sine ky plus D cos ky into e to the power minus j beta gz. So this is the solution for this equation that we discussed in the previous lecture of solution of wave equation for rectangular waveguide. Now on the basis of this solution, if we write down the solution for this equation number 1, then its value will become E of z, that is being equals to am sine kx plus bm cos kx into cn sine ky plus dn cos ky into e to the power minus j beta gz. Now if we apply the boundary conditions, then after applying the boundary condition, applying boundary condition. We have to replace this kx, that is k subscript s, with m pi over a, and also this k subscript y with n pi over b. And after replacing this k subscript x and k subscript y in this expression, we get the value of E of z as Ez, that is equals to am sine m pi x over a plus bm cos m pi x over a in multiplication with cn sine n pi y over b plus dn cos n pi y over b in multiplication with e to the power minus j beta gz. So this is the solution for the E of z. This is our equation number 2. Now let us have a look at the Maxwell's equation in frequency domain. So Maxwell's equation in frequency domain for electric field is given as del cross E, that is being equals to minus of j omega mu into h. This is the condition for lossless dielectric. We know that here the value of del is equals to del over del x into I cap plus del over del y into j cap plus del over del z into k cap. Similarly, if we write the value of this electric field intensity in the vector representation, then it will be equals to Ex I cap plus Ey j cap plus Ez k cap. Now if we write the vector representation for magnetic field intensity, then it will be equals to Hx I cap plus Hy j cap plus Hz k cap. Now this is our equation number 3rd. If we substitute the value of del, E vector and H vector in the equation number 3rd, then it will become del over del x into I cap plus del over del y into j cap plus del over del z into k cap, that is in cross product with the value of E vector, that is here. So Ex I cap plus Ey j cap plus Ez k cap, that is equals to minus j omega mu. In place of this H vector, we will write this expression, that is Hx I cap plus Hy j cap plus Hz into k cap. Now we have to solve this cross product. So for solving the cross product, we have to take the determinant. So this is the component for I cap, this is j cap, this is k cap. Now we have to write the coefficient of I cap, j cap and k cap. So here are the coefficient of I cap, j cap and k cap, that is del over del x, del over del y, del over del z. Similarly, for the electric field component, we write Ex Ey and Ez. That is nothing but equals to minus of j omega mu hx I cap plus hy j cap plus hz k cap. Similarly, if we solve this determinant, then its value will become equals to I cap del over del y into E of z minus of del over del z into E of y minus of j cap del over del x of E of z minus del over del z of E of x plus k cap del over del x of E of y minus del over del y of E of x, that is equals to minus of j omega mu hx I cap plus hy j cap plus hz k cap. Now, if we compare the coefficient of I cap, j cap and k cap on both the left hand side as well as the right hand side, then we get, on comparing coefficients of I cap, j cap and k cap, we get, on comparing the coefficient of I cap, we get del over del y into E of z minus del over del z into E of y, that is being equals to j omega mu into h of x. Here is minus sign. So minus of j omega mu into h of x. This is our equation number 4. Similarly, on comparing the coefficient of j cap, we get del over del z into E of x minus del over del x into E of z, that is being equals to minus of j omega mu into h of y. This is equation number 5. Similarly, if we calculate and compare the coefficient of k cap, then it will be equals to del over del x into E of y minus del over del y of E of x, that is equals to minus j omega mu into h of z. This is equation number 6. So these are the 6 expressions that we get after comparing the coefficient of I cap, j cap and k cap. Now let us have a look at the Maxwell's equation for frequency domain in case of magnetic field. So the Maxwell's equation in frequency domain is given as del cross h, that is being equals to j omega epsilon into E. If we write down the value of del, h vector and E vector in this equation, and after substituting, we will compare the coefficient of I cap, j cap and k cap as we did in the Maxwell's fourth equation. Then on comparing the coefficients of I cap, j cap and k cap, we get the expression after solving, that is being equals to del over del y into h of z minus del over del z into h of y, that is being equals to j omega epsilon into e of x. Similarly, if we compare the coefficient of j cap, then we get del over del z into h of x minus del over del x into h of z, that is being equals to j omega epsilon into e of y. And if we compare the coefficient of k cap, then we get del over del x into h of y minus del over del y into h of x, that is being equals to j omega epsilon into e of z. This is our equation number 7. This is our equation number 8. This is equation 9 and this is equation 10. So these are the expression that we get after comparing the coefficient of I cap, j cap and k cap on both the LHS as well as in the RHS. Now let us apply some boundary conditions in this 6 equations, that is 8, 9 and 10, and also we have discussed the equation 4, 5 and 6. So substituting del over del z, that is being equals to minus of j beta g, and hz equals to 0 in equation 4, equation 5, 6 as well as 8, 9 and 10. So after substituting del over del z equals to minus j beta j and hz equals to 0 in this equation, we get our modified equation as del over del y of e of z plus j beta g into e of y, that is being equals to j omega mu into h of x. This is the equation that we get after applying this boundary condition in equation number 4. Similarly, from equation number 5, we get j beta g into e of x plus del over del x into e of z, it is being equals to j omega mu into h of y. On applying the boundary condition in equation number 6, we get del over del x into e of y minus del over del y into e of x, that is being equals to 0 only. From equation number 8, after application of boundary condition, we get beta g into h of y, that is equals to omega epsilon into e of x. From equation number 9, we get minus of beta g into h of x equals to omega epsilon into e of y. And from equation number 10, we get del over del x into h of y minus del over del y of h of x equals to j omega epsilon into e of z. Now these are the 6 equations that we get after application of these boundary conditions. If we solve this equation and find out the value of this component, that is ex, ey, ez, hx, hy and hz in terms of hz only, then the solution for this equation is given as for the value of E of x, it will be equals to minus of j beta g over kc square del over del x into E of z. For the value of E of y, it will be equals to minus of j beta g over kc square del over del y of E of z. For the value of h of x, it will be equals to j omega epsilon over kc square del over del y of E of z. And similarly, if we calculate the value of h of y, then it will be equals to minus of j omega epsilon over kc square into del over del x of E of z. And since we assume that the value of hz is equals to 0, so hz is equals to 0, and here one component is missing, that is Ez. So if we write down the value of Ez, so it is nothing but the expression that we evaluated earlier, which is equals to am sin m pi x over a plus bm cos m pi x over a into cn sin, and here is n pi y over b plus dn cos n pi y over b e to the power minus j beta gz. So these are the 6 values for the components. Let us give it as equation number 11, equation number 12, equation number 13. Here is equation 14. Here is equation number 15, and this is final equation, that is 16. On the basis of this 6 equation, we can say that the boundary condition for the E of z require that the field vanishes at the waveguide walls, or we can say that since the tangential component of electric field, that is E of z, is equals to 0 on the conducting walls, there is a requirement like we have to apply the boundary condition. So according to the first boundary condition, since we know that the value of E of z is equals to 0 at x value, that is equals to 0 and x equals to a, this implies that the value of the component, that is b of m, will be equals to 0 only. Here x equals to 0 represents the LHS or the origin side of rectangular waveguide, and x equals to a represents the right hand side of rectangular waveguide. Similarly, according to the boundary condition second, that is E of z, that is equals to 0 at y equals to 0 and y equals to b. Here y equals to 0 represents the bottom wall of rectangular waveguide, and y equals to b represents the top wall of rectangular waveguide. And if we note down the conclusion from this second boundary condition, then it will result into the dn component, which is equals to 0 only. So on the basis of these two components, we can give the solution for the equation as solution is given as E of z, which is being equals to E of 0z sine m pi x over a sine n pi y over b into e to the power minus j beta g z. This is the equation that we get for the expression of E of z after substituting this bm equals to 0 and dn equals to 0 in our equation number 2nd. So we have also evaluated the 6 components, that is Ex, Ey and Hx, Hy and Hz in terms of Ez. So on substituting the value of Ez in all the 6 components expression, we get, substituting the value of Ez in equation number 11, 12, 13, 14, 15 and finally 16, we get the value for each and every component as, for the value of E of x, we get it value as E of x, that will be equals to E of 0x cos m pi x over a sine n pi y over b e to the power minus j beta gz. Similarly, for the value of E of y, we get E of 0y sine m pi x over a cos n pi y over b e to the power minus j beta gz. Similarly, the value of h of x is given as h of 0x sine of m pi x over a cos of n pi y over b e to the power minus j beta gz. Now the value of h of y is equals to h of 0y cos m pi x over a sine n pi y over b e to the power minus j beta gz, and the value of hz is equals to 0 only. So these are the 5 components, and here is the 6th component that we evaluated after putting bm equals to 0 and dn equals to 0 in equation number 2nd. Now let us have a look at the parameters that are associated with transverse magnetic mode in rectangular waveguide. So discussing about the parameter 1, that is cutoff frequency. See, the cutoff frequency is denoted by Fc, and the expression for Fc is equals to C over 2 under the root m square over a square plus n square over b square. Moving on to the next parameter, that is propagation constant. So the propagation constant in transmission TM mode can also be represented as beta g, that is equals to omega under the root mu epsilon under the root 1 minus Fc over F whole square. And the third parameter is given as wavelength, that is denoted by lambda g. Where the expression for the lambda g for transverse magnetic mode is given as lambda over under the root 1 minus Fc over F whole square. And finally, the last parameter associated with TM mode is given as phase velocity. And the phase velocity is denoted by Vg, that is being equals to Vp over under the root 1 minus Fc over F whole square. So these are the solution for the 6 components that are associated with transverse magnetic mode and also the parameters associated with TM mode. So this is all about the TM mode. If you like my videos, then do subscribe my channel and please hit the like button. Thank you.